So I mentioned today we're going to start looking at the inside of the engine and the different assemblies, how we break them down, what we call them, and what their function is. So when we look at a typical engine, piston engine, we're looking at two main assemblies. One is what we call the bottom end. So the bottom end is going to contain my crankshaft, bearings, connecting rods, pistons, oil pump. That's going to be my bottom end. My bottom end may also have my camshaft in it, depending on whether the camshaft is in the cylinder head, which would be the top end, or in the block, which is the bottom end. So that's going to come down to engine design. Older engines all had the camshaft in the bottom end. As we started introducing overhead cam engines 40 years ago, 40 plus years ago, actually, we start seeing the camshaft move to the top end. So that's going to determine on engine configuration. The crankshaft, connecting rods, flywheel, harmonic balancer make up the rotating assembly that's part of the bottom end. So even though my flywheel and harmonic balancer normally don't come with my bottom, they're not considered an internal part of the engine, they're bolted to it. They are part of that rotating assembly, and that's part of the balance of that rotating assembly. So one of the things we do when we rebuild an engine is we have the opportunity of balancing the engine, and that normally costs additional money. And the advantage of balancing is it gets rid of harmonic vibrations, which allows the engine to last longer. In order to balance the engine, we're actually balancing the flywheel all the way through the harmonic balancer, the crankshaft, everything, to make sure that there's not a heavy spot as it rotates. Engines that come from the factory are not precisely balanced. They're kind of close to balance. So all harmonic balancers have a certain balance or weighting to them based on engine design. And so when we pay to have something balanced, we're really talking about fine tuning. Same with the flywheel. So this is something that you run into occasionally where engines can be internally balanced or externally balanced. So in other words, they may be balanced inside and the flywheel just bolts on it, or the flywheel is part of the balancing process. And we saw this on 5-liter Ford V8s, the difference between a high output engine and a normal engine. A normal engine is internally balanced, where a high output is externally balanced. So if you put the incorrect flywheel on, the vehicle has a horrible vibration. So that's something to consider. That's why we mark flywheels before we take them off. That's not an issue with flex plates with automatic transmissions. It's really only an issue with manual transmissions, but it could be with a flex plate. Flex plates do have weights on them. So it's always best practice to mark and make sure you put it back on the same way you took it off whenever possible. If you're replacing the flywheel, then obviously that's not an option. But if you have a vibration afterwards that you didn't have before, you got to suspect the flywheel you put on could be contributing to that problem. And that's pretty common on some vehicles after doing a clutch. My top end consists of the cylinder heads and the combustion chambers. So they are going to contain on any close to modern vehicles, going to contain my valves. Like I said, we don't have any engines we used on automobiles since 1966 that didn't have valves in the head. My valve train may be confined to the cylinder head, or my valve train may be connecting my bottom end to my top end. So it depends on where the camshaft is. If the camshaft's in the block, then I'm going to have a valve train that connects that camshaft up to the valves in the head. If the camshaft's in the head, all my valve train is going to be in the head. So it also contains the camshaft. So you can see here in this illustration, I can see the bottom end here and the top end here, and they're separated by the head gasket. So when we buy an engine, I can buy the bottom end, the top end, or the bottom and top end together, and those have different names. So a short block replacement includes all the parts of the engine block below the head gasket to above the oil pan. So that's a short block. So a short block is going to have my crankshaft, pistons, connecting rods, all those things in it. No cylinder head gasket, no oil pan, none of those things. So a cam and block engine includes the camshaft and timing gears, where an overhead cam will not include the timing gears or the camshaft.
Mr. Brian,
Yes.
I'm still marinating on the flywheel. So how does a technician doing a clutch on a stick shift transmission is gonna balance the the flywheel if it's changing the flywheel?
Well, you're
Maybe.
not, and that's why it's really important to make sure you get the correct flywheel. So something as simple as I'm working on a Ford Mustang and it has a 5 liter, but is it the 5 liter HO or the 5 liter regular? And I'm too lazy to check, and I just say, hey, give me the one for the 5 liter, or maybe the parts guy makes a mistake. And those are very different engines. They have a different firing order. I mean, they're very, very different engines. So that's the one that comes to mind where we've seen the problem. For the most part, it's not an issue. Many flywheels are indexed to only go on one way on modern vehicles. So if we're putting on a flywheel that is manufactured to the manufacturer specifications for how it was assembled at the factory, it's not going to be an issue.
So there are markings.
What's that?
Are there markings?
Not so much marking. The bolts are not evenly spaced. So on some flywheels where you have 6 bolts holding them on, 2 of the bolts may be closer together. So you can only bolt it on one way.
Oh, okay. Okay, understood.
So that is, so some of it makes it kind of, I can't screw this up. Other ones will spin on anyway. And if I'm replacing the flywheel, I just have to assume I got the right one, make sure it got cataloged and sent to me correctly, put it on, I should be fine. Where we run into issues is if someone has balanced the engine, maybe I'm working on a, early 70s, late 60s hot rod, something like that. Or if the parts house gives me the wrong one. And that's why I bring it up, because, if you read enthusiast magazines, they talk about balancing an engine, they talk about these things. What is that? Well, all engines come balanced from the factory. They're just balanced how we would balance if I need to make 100,000 engines. Right? They're not taking the time to really get each one exactly perfect. They're just within tolerance.
Right.
When they balance something that you pay that extra $100 for when you're having an engine built, they're actually balancing it exactly. They're taking that tolerance down to a lower level. So they're not really completely changing it, but they're looking at the whole thing and making it really balanced. So what happens occasionally is when someone changes the flywheel on one of those engines, now there's a little vibration that wasn't there before, and the customer's upset because obviously they're an enthusiast or it's their pride and joy and they've spent money other places. And that's why it's important. Also, if I'm doing a clutch on a 72 Chevelle, and this is a nice car, and the guy's telling me about all the stuff he did, I might want to take that flywheel out and have his flywheel resurfaced versus exchanging the flywheel with a resurfaced flywheel or a rebuilt flywheel or putting a new flywheel in. So because, hey, I want to make sure I get that same flywheel back and do that. And so therefore, I'm going to need the car an extra day or two because you have a special car. If I'm doing a 96 Honda, I'm not going to think twice about it. I'm just going to be swapping it through, or a 2005 Honda or whatever I'm doing a collection. I'm not going to think twice about it because I'm just not going to run into issues there. But I think, you remember we talked about there's very few things that are always and never. I think part of, class is to expose you guys to different things that I've seen cause issues over the years. And that way you can pay attention to what you're working on. Am I working on someone's daily driver? It's a 2005 Honda that needs a clutch. I'm just going to get the, correct parts for it, put it in. I'm not going to have a problem. I'm working on someone's performance vehicle, or I'm working on someone's, 94 Corvette, and they're telling me about all the stuff they've done and it's custom. Maybe I want to reuse their flywheel and get it surfaced and do that as opposed to treating it like I would someone's transportation car. Does that help, Dante?
Oh yeah. I'm gonna be helping my brother do his Dodge Ram. I don't remember the year. Transmission clutch.
Okay. So on the Ram, and this is not a transmission class, so I don't want to go too far down. On some of the Rams, they use what's called a dual mass flywheel. Normally, they used them only on the diesels, not on the gas engines. But if you pull out a flywheel doing a clutch and it's not just one solid piece of metal, but it's two different pieces of metal, and they
Uh-huh.
move back and forth with rubber bushings, that's called a dual mass flywheel. You normally want to replace those. However, those can be very, very expensive. So take that into account. I don't
will.
think the gasoline Dodges use that, but if you run them and go, wait a minute, this isn't a solid piece of metal. What you never want to do is take out the dual mass and put in a regular flywheel that's just a single piece of metal.
Got
Because that's part of vibration process. And like I said, this is not a transmission class. I don't want to get into it.
Right,
We
right.
cover that in the 507 class, which is brake suspension and transmission service. But I did want to at least bring that up since you're going to be doing that.
Well, I took 507. I don't recall going in depth in the. This is why I'm asking. I don't recall. Maybe I forgot.
Right. Yeah, I don't know. I didn't sit in the class, but I know it's in the curriculum for that class, so they're supposed to cover it.
Very well.
So I know when we laid out the curriculum for the program, that's whose hat that was in.
Right.
Because not that I don't know it, it's just I've already got too much stuff in my hat here, and that's why your guys' head hurts.
Thank you.
You bet. So here's an example of a short block and a long block, and these are not precise necessarily from what I expect to see. I'll explain what I mean in a minute. So here is a short block which has no cylinder head, but normally a short block won't have this oil filter assembly on it either, and normally won't have a harmonic balancer on it either, unless there's some special engines you have to put the harmonic balancer on because it actually holds things together inside. But that's the exception and not the rule. So normally I wouldn't get this. I would just have the block assembly with the crankshaft, the pistons, and you can see the top of the cylinder bores here. A long block would have the engine block, in this case, the camshaft and the crankshaft, timing chain, my cylinder heads, all my valve train is connected. I would not get spark plugs with it. I would not get an intake manifold with it. So this is not a long block. This has more things on it. You can see there's even a valve cover over here. I'm not going to get a valve cover with a long block. So what a lot of manufacturers have now done, because cleaning the engine in the shop is an issue. So what we used to do is we used to get a short block or long block. We pull off what we call the tin, which is your valve cover. You can see right here, oil pans, timing covers. We pull all that tin off, clean it in the shop. So as we are cleaning the shop, what we found is a lot of shops didn't clean it well. And so engines that were put in were failing because of contamination, because parts were not cleaned effectively. So what some manufacturers have gone to is selling a complete engine. So Ford does this, GM does this. And so that's an engine that comes with all the tin. It comes with the oil pan on it, comes with the valve covers on it, may come with the spark plugs already in it, timing covers on it, does not come with the intake manifold, but it's pretty well sealed up. And so that's going to save you a couple hours of disassembly and cleaning and transferring of parts and gaskets and all that stuff. So it makes a lot less work for the technician. It also provides a better product to the customer because everything in there has been cleaned at the factory much better than I'm going to be able to clean it in the shop. And so it's a sealed, it's a more of a sealed assembly. So a lot of manufacturers have gone to that because they've seen the extra money they're spending to put all the tin on at the factory and maybe raise the price $50 is more than made up for by the amount of engines that they're having to do again because they've been damaged by inefficient cleaning or using the wrong products for cleaning, like a roll-lock disc and getting fragments of what we call a roll-lock disc. It's a round 3M Scotch-Brite disc. And that if that gets in oil passages, it destroys the bearings. So people use that. Now the engine goes bad in 1,000 or 2,000 miles or less because that material got into the engine. So that's why manufacturers started doing that. So when I look to buy an engine, I can get a short block, I can get a long block. Some long blocks, it may be called a long block, but it comes as a complete. Other manufacturers specify, no, this is a complete, meaning it has the tin and all that. So anytime you're buying an engine, you should always ask, does that come with, if you're buying a long block, ask them, does that come with the tin? Does that come with the covers? Because that's going to make a big difference in how much time you're going to spend. It also makes a big difference on, because of the amount of cleaning you do. If I want to clean the valve covers, oil pan, all that stuff, I probably need a solvent tank. I need some stuff to even try to get the stuff close to clean. On the other hand, if it comes with all the tin already on it, I'm not cleaning any of those oily surfaces. I'm down to putting the new water pump on, I'm doing very little cleaning because the engine's clean. The new water pump I'm putting on is clean. I might need to clean the intake manifold off a little bit. Some manufacturers like Chrysler on the Hemi require you to buy a new intake manifold or they won't warranty the engine. Again, I'm a lot less. On the other hand, if I have the ability to do the cleaning, if I'm comfortable with that, if I'm comfortable with assembly, but I don't want to, might not be comfortable with putting the pistons in and the bearings in and all that stuff. I don't want to rebuild the whole engine, but I want to save some money. Many times you can get a short block assembly and get the cylinder head rebuilt and then assemble the cylinder head on the short block assembly yourself. And many times you can save a fair amount of money, even if you're having the same machine shop, rebuild the bottom end and do a short block and rebuild the cylinder head and do a valve job. The fact that you're putting those two things together and not them often can save you a couple $100. I mean, that's a pretty big savings for basically putting on a couple cylinder heads and connecting the valve train and doing those things. So that's where you don't need to get in that machining. You don't need all the micrometers. You're not honing things out. You're just assembling, but you're able to save some money assembling to get, so you're buying that short block and having them do the head versus having them do the long block. So it pays to price it both ways if you're having your engine rebuilt. So that's where it gets confusing. What am I buying? If I go to a shop, what am I buying? Well, if someone says they're selling you a new engine, odds are they're lying to you because you can't buy new engines for the most part. Almost everything we buy is a rebuilt or remanufactured engine. Sometimes it'll be a remanufactured dash new because based on what they did during the remanufacturing process, they can call it remanufactured new, but it is not new. So we're not buying a new engine, just like we're not buying a new transmission. For the most part, we are buying a rebuilt unit or a remanufactured unit. They don't have a bunch of brand new engines that were left over from when they made your car 10 years ago or 20 years ago that are just waiting for you to call and have it delivered. Those don't exist. So these are normally rebuilt assemblies. So it's new to you, but it's not a new engine normally. So my cylinder block is the largest single part of the engine, normally made of cast iron or aluminum. The block casting includes the cylinder bore opening. So I can see where the cylinder bore is here, 1, 2, 3, 4. That's where my pistons are going to be. I have coolant jackets or water jackets that go around the cylinder bores because the sides of the cylinder get very hot. And so that heat transfers to the walls of the cylinder, and then that heat transfers to the coolant, which is circulated through the engine, which goes to the radiator, and then that heat energy is transferred to the air. The crankcase is the lowest portion of the block that houses the crankshaft. That's really kind of changed a little bit in definition over the years. The crankcase is largely considered any part of the engine where oil is traveling, where it's not under pressure, but is sealed from the atmosphere. So inside my valve gubbers is part of the crankcase because that's where I have crankcase vapors that I have to control for emission requirements. So the crankcase now is really considered the entire inside of the engine where oil travels that's not under pressure. And that's really what we consider the crankcase. The definition of the crankcase being the lowest part of the block that houses the crankshaft is a very, very old school definition of a crankcase, really pre-emission. So we're jumping in the Wayback Machine about 70 years. Or if not longer. So little difference there on what the book's explaining. The oil pan completes the crankcase. The bed plate, which is an engine girdle, which the main bearing caps are part of. So not all engines use a bed plate. Many modern engines do. They do that for stiffening and so that they can use lighter materials in the block. On older engines, we'd see what we have here, which is without a bed plate, where these bearing caps would bolt directly to the block. So when I look at my crankshaft, as I mentioned yesterday, I have two kinds of journals. I have my main journals, which are in a straight line. And I have my connecting rod journals, which attach to my connecting rod, which we're going to see attaches to the bottom of the piston, which is when the piston produces power, it moves that around and provides leverage to spin the crankshaft. The main journals are in a straight line. All they're doing is spinning. So, which journals go out first? Well, normally the connecting rod journals are the ones that go bad. So if I have a bearing failure on the crankshaft, most of the time it's a connecting rod bearing. And you may have heard the term you spun a bearing or you threw a rod bearing. That's what they're talking about, is the bearing that rides on this journal. A flywheel is a weighted assembly that stores kinetic energy from each power stroke and helps keep the crankshaft turning through the non-power strokes. So we were talking about yesterday, your lawnmower has 4 strokes. The crankshaft has to go around 2 times. It only gets power, once out of every two revolutions. Your engine's a little smoother. We got 4 cylinders, so I'm firing a cylinder every 180 degrees of crankshaft rotation. But I want smooth power. I don't want this surge of power, surge of power, surge of power. So what we use is a flywheel to store kinetic energy, because once we get that rotating mass is going to keep that engine spinning. And it also allows that downward stroke of the piston, the leverage on the connecting rod over the crankshaft as it spins, it's now accelerating that mass slightly. And then that mass is going to slightly decelerate till the next time it's pushed. Just like the merry-go-round with kids on it on the playground. As you spin the merry-go-round, you spin it, it's going to slow down slightly before the next bar comes by and you can spin it again. But the mass of the merry-go-round, that big metal mass that was hard to start spinning, is now very easy to keep spinning because you have the weight of that mass continuing that motion. So now we're basically just maintaining that motion, which makes it very smooth. So that is where we have that acceleration. So, many engines that are fairly small engines used for industrial applications might have a very, very large flywheel. If we, again, going back in the Wayback Machine, over 100 years, farm tractors made very little horsepower, but they had a flywheel that weighed hundreds of pounds. So once they got that going, it was the kinetic energy of that flywheel that allowed the tractor to be doing all these things, even though it was a very, very small horsepower engine. The tractor I have here at the house, again, only 20 horsepower tractor, but yet it has a flywheel. It has things in it that allow it to store that kinetic energy. Even something down to my chipper for when I have to trim brush and I chip the chipper. The chipper has a 150-pound flywheel in it. So when I feed, a 3-inch piece of brush into the chipper, instead of stalling the engine on the tractor, the kinetic energy of that big flywheel is able to slice through, even though it may bog down a little bit. That kinetic energy allows it to keep moving and keeps the motor from stalling. So we store energy in that flywheel. Now on an automatic transmission, I don't have a heavy flywheel. I have what we call a flex plate, which is a thin piece of metal with a ring gear on it for the starter to connect to. However, with an automatic transmission, I also have this big torque converter full of fluid that's very heavy. So the torque converter is what is enabling that kinetic energy, and it is bolted to that flex plate. So on a manual transmission, we can have a pretty heavy flex plate. On an automatic transmission, we use the weight of the fluid and the weight of the torque converter to accomplish that's basically the same task. And then depending on applications, if I want torque, I'm going to want a heavier flywheel. If I want horsepower, I'd want a lighter flywheel. So, again, you get into race applications. What are you trying to do? Are you trying to go a quarter mile really fast, or are you trying to rock crawl and you want your engine at 600 RPM? You're going to have different demands, different desires for what you want out of that flywheel. So for some applications, I can buy different flywheels, or I can machine a flywheel down to make it lighter for certain types of racing applications. So it's really interesting, when you start thinking about the energy, the engine's making the energy, but how am I storing it? How am I using it? So that's why this is our rotating assembly. Same thing with the harmonic balancer. The harmonic balancer has a rubber layer between where the pulley rides and the crankshaft is. And that allows some shock absorption between all the pulleys that are connected with the belt and the crankshaft itself. So harmonic balancers also, they can come apart, and this rubber will actually start to spit out. I've seen them come apart completely. I've also seen them spin, where you get some interesting vibration issues, or you try to check timing and the timing doesn't check. So harmonic balancers can either spin or come apart. So they do fail. Connecting rod and piston. The connecting rod connects the piston to the crankshaft and transfers the piston movement and combustion pressure to the crankshaft rod journal. So here is my connecting rod. My connecting rod goes to the piston and is held with a wrist pin. And then we have our connecting rod. All right, here has the two halves. There's a bearing inside here, and the bearing is mounted to the connecting rod and spins on the crankshaft journal, because there's a layer of oil between the bearing and the crankshaft journal. And we'll look at that a little more when we get to lubrication. So here I'm at top dead center, bottom dead center, top dead center. What I don't like about this picture is it doesn't show halfway. And what happens is, because here's the center that we're spinning on, this is off center. As this comes down, it's going to go around this way. But when this journal is over here, when this journal is over here, this is no longer straight up and down. This has to pivot. So this has to move this way to allow the rod to move this way for when the journal is over here. So the connecting rod is going to pivot here on the wrist pin. It's going to pivot here on the connecting rod bearing. So our piston itself is going to have either 2 or 3 upper rings, and then it's going to have an oil control ring. So most cars have 2 rings. Performance pistons, performance applications for gasoline vehicles will have 3 rings, and diesels tend to have 3 rings. So these rings fit inside the grooves of the pistons. And so I have 2 compression rings, and then I have an oil control ring. So the oil control ring does a couple things. It allows me to put oil onto the walls of the cylinder, because as the piston goes up, I want to put some oil on the cylinder wall, so when the piston comes down, it has lubrication on the walls. Otherwise, I'd have just metal on metal rubbing together, and my engine wouldn't last very long. But what I want to make sure I do is only put a certain amount of oil there. I don't want to put too much. So that's why we call these our oil control rings. I don't want to just have lots of oil, because then I'd use too much oil. My car would even smoke potentially. So I want to leave a very fine film of oil as it goes down. So we have 2 different things going on here. I have compression rings. If my compression rings go bad, I'm going to lose compression in the cylinder. I'm going to have low compression. I'm going to have an engine that runs unevenly. If I have oil rings go bad, I'm going to use a lot of oil. So I can still have really good compression, a car that doesn't smoke because I'm actually burning all the oil I put in the cylinder, but a spark plug that might foul prematurely or something like that. But yet I'm using a lot of oil. I can also have a car that has weak compression rings, low compression, engine runs bad, but good oil rings, and I'm not using a lot of oil, but I have a bad cylinder. So even though they're both rings, they perform two very different functions. So these oil rings, I've got a picture of a real piston here. So here's a piston I'd laying around. So this one is a performance piston out of a little British sports car, I think it is. Is it British or Japanese? But I think it's British. So 1, 2, 3 compression rings. And then here's my oil control ring. And you can see it has 2 little wiper rings and a place for oil to sit in the middle. This is my ring gap right here. So my ring gap, and here it looks huge because the piston's not installed in the cylinder. There is a specification for how close those ends are supposed to be. So what we do is we take a ring, put it inside of a cylinder bore, and use a feeler gauge and measure the ring gap against specifications. If the gap is too big, then I need to use different rings. It usually means that the cylinder has worn out and the cylinder needs to be resized, and I need to use oversized rings. If it is too little, then I need to take a file and file the opening in the rings till it's just the right size. And the reason why we need a little bit of a gap is because this is all metal parts. They're going to expand and contract. So if I had no gap, as soon as they get hot, things are going to expand. It's going to push its way out, and it's going to score the side of the cylinder. And I'm going to have a compression and an oil usage issue. If it's too far apart, if I have too much ring gap, now I have too much compression pressure blow past the ring gap, causing low compression in the cylinder. So this is one of the critical measurements we have when we're replacing rings on an engine. Also, the oil control rings are very susceptible to contamination. So if I have a car, I'm supposed to run a certain kind of oil, and I need to change that oil at a minimum frequency. If I fail to do either of those things, I will get heavy carbon deposits in my oil rings here. Once I get the carbon deposits in the oil rings, my car will start using oil. And changing the oil doesn't fix that. Normally, nothing will fix that. So congratulations, you've just ruined an engine with 70,000 miles on it that now goes through a quart of oil every 500 miles. Oh, did I mention it takes synthetic oil and you're supposed to change it every, 7,000 or 10,000, whatever the manufacturer recommended. So what we see happen is, I'll use BMW as an example because they're easy to pick on. BMW 6-cylinder holds 7 quarts of oil. Manufacturer says an oil change is only required every 7,000 to 13,000 miles, depending on the type of driving you do. And they have a system that comes on and tells you to change the oil. BMW also says it's normal to use a quart of oil every 700 miles on a good engine. So let me do the math. I can use a quart of oil every 700 miles. I can go 7,000 miles minimum between oil changes, according to BMW. That would be 10 quarts of oil. I left the service facility with only 7 quarts of oil in my engine, and a quart of that's going to be tied up in my oil filter that I really can't use. So now I'm down to really 6 quarts I can use. I'm going to run low on oil before I get to my oil change. As we run low on oil, the car runs hotter, because oil is one of the things we use to dissipate heat, cool the engine. So now, as I run hotter, now I start to burn the oil on the oil rings. Now the oil rings don't hold oil correctly, don't control oil usage correctly. So guess what? Now I'm using more oil. So it becomes cyclical and gets worse and worse. And so what we see is customers will drive and their oil light comes on, or the oil light comes on because they lost oil pressure. Some cars have a level sensor, and a level sensor comes on and tells them they're low on oil. And they're like, well, I'm not due for an oil change for another 5,000 miles, right? That's to change the oil. That's not to check the oil. For some reason, people think that they should never check the oil between oil changes, and that's just not realistic on a lot of these vehicles. And the consequences of running a car low on oil are catastrophic for the overall life of the engine and also the overall life of how much oil you're going to go through. So, for example, my Toyota really doesn't use, I still don't use a quart of oil in 5,000 miles. I use very little oil. I just checked my oil this morning because I got to go up to Santa Ana to teach a class tonight. And my oil is still basically full. And I've got over 2,000 miles on since I changed the oil. So I'm still in great shape. My daughter's car, and she bought a Honda product, she bought an Acura, she goes through a quart of oil every 1,000 miles, has since it was new. So imagine if she hadn't, and Honda says that's okay. Imagine if she hadn't checked her car and she was going 5,000 miles between oil changes.
Mr. Brian,
Yeah.
I heard this, I haven't verified. Does the PCV valve, when it goes bad, does it influence oil consumption?
It can, depends on how it goes bad. So we are going to talk about the PCV system when I get into emissions, and we'll get into that a little bit deeper. So it can affect oil consumption. It may not necessarily. A lot of times when we see too much oil going through the PCV system, it's not a valve problem or a control problem. It's what we call a blow-by problem. And that is where our compression rings are not sealing correctly. So we're putting too much pressure into the crankcase, which is causing oil to get pushed through the crankcase ventilation system. Very common on turbocharged vehicles or supercharged vehicles.
Thank you.
I had a question, but I think it was kind of answered. When you say that oil is being, there's less oil, I didn't know. I wasn't sure if you meant like there was actually less, or that the quality of the oil was diminishing. But is it both?
It is both.
Okay, and I was wondering too if the oil. I thought it was kind of a closed circuit. So other than like an obvious oil leak, how do you lose the oil? But now I think I know the answer. It's because it goes through the pistons. And so little bit by little bit, it's kind of dissipating. Is that right? Absolutely.
Yeah. So all engines use oil. So when someone comes and says, my car never uses a drop of oil. Well, you don't understand how your car works. It has to use oil. What we want to use is a very small amount of oil, ideally. And we do many things that we've changed technology in the last 30 years to do that. We now use what are called low tension piston rings. So they're not putting as much force on the cylinder wall. So I don't need to put as much oil there to keep them from gouging the cylinder wall. So there's a lot of technology that's evolved, not just over the last 30 years, over the last 10 years, over the last 50 years. A car today is different than a car yesterday, but certain things are still true. We're still going to use a certain amount of oil. We have to, because we have to lubricate these piston rings as they go up and down the cylinder wall. Otherwise, we would just have this metal on metal scraping and it wouldn't last long. Oils do break down. So when we look at oil, there's two parts of oil. There is the base oil, which may be coming out of a laboratory or it may be coming out of the ground. And then we have additives that we add to that to give oil certain characteristics. So the additives break down, and then what we call the base stock or the oil also breaks down. So oil that comes out of the ground breaks down at a much higher rate than oil that comes out of a laboratory. So oil that comes out of a laboratory is a synthetic oil. Oil that comes out of the ground is a conventional oil. But both of those have additives to give different characteristics that we need from the oil. And we're going to get into that a little bit more on lubrication. Oil is always fun to talk about because it's something that everyone has experience with in the class. And so oil and lubrication and coolant and cooling systems are usually two of the best conversations of the class.
Got it. Thank you so much.
You bet. Great questions. And I'm sorry I didn't hear you pop up with a question, Rebecca.
Oh, no, that's okay.
So This ring gap, obviously, if we're putting 3 rings in, we don't want to line our ring gaps up because that's just like a freeway for the combustion gases to go through. We would index them. So if I have 2 piston rings that are compression rings, they're going to be 180 apart. 3 of them, I'm going to clock them so they're evenly spaced around the circle. So 360 degrees, divide the 360 by 3. So every 120 degrees, I want the gap. So I want to evenly space it. Also, as the oil rings become congested, the next thing that happens is we start getting oil and carbon deposits into the piston rings. The piston rings have to be free to move slightly. They have to be able to expand and contract. They have to be able to ride as the piston is pulled down. It's also pulled slightly to the side, right? Because it's not a straight up and down. It has force going both ways. So the rings need to have some flexibility in them. They need to be able to move a little bit. If they get gummed up, they can no longer move. We start losing compression. We also start using more oil. And that's usually when that happens, is usually when we start seeing smoking from the rings, because we've already lost the oil control rings. Now we're sacrificing the piston control rings and we're starting to get smoke. That is not the number one cause of cars smoking today, but that's what happens when we start getting smoke from the rings.
I did that back I was a teenager in the 90s. I used to own a Mitsubishi Mighty Max, and I did the engine pistons, and I left compression rings lining up. I did that mistake. I was a teenager back then.
Yeah, but that's a mistake a lot of people make. And that's why I mentioned it in the class, because it makes sense, right? A lot of things we line up, when we're putting something together, and the directions aren't clear. If you're following directions in the manual, they just say, put them on. Okay, great. They really don't explain the indexing or explain why we do certain things. And that's why I kind of try to touch some of those high spots here. So even if I'm never going to rebuild an engine, at least I can figure out either what someone else did wrong, or I can figure out what may have happened from lack of maintenance or improper care or just normal wear and tear. That's a symptom I'm diagnosing outside the engine. I think it's helpful to understand what's going inside to figure out, hey, what's actually causing the problem here. So, yep, you're not the first person who's made that mistake, Dante. You won't be the last. The crankshaft is what causes the piston to move up and down. Is that true or false?
True.
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 Absolutely.
Okay, true.
And the key word there is up and down, right? I can argue that the compression, the explosion we have under compression pushes the piston down, but it certainly doesn't make the piston go up. So the only thing that makes it go up and down is the crankshaft. To think about it, I got to go up for the compression stroke before I can ignite it, and then it's going down. And certainly, ideally, down is being powered by the explosion in the combustion chamber. But reality is, if I'm cranking the engine over and it doesn't start, my piston's still going up and down, and I'm not even burning any fuel. So you guys got it 100% right. The crankshaft is what causes it to go up and down. The rings in the lower part of the piston are used to control which of the following?
Number 2.
Oil.
Number 2, oil. Absolutely.
Yep.
The component that goes between the crankshaft and the piston is called what?
Number 2.
Connecting
Number
rod.
2, connecting rod. You got it. So now let's talk a little bit about our cylinder head. So cylinder heads can be constructed of cast iron or aluminum. Vehicles today use aluminum cylinder heads. Back when I started this business, almost everything was a cast iron cylinder head. And let me tell you, cast iron's a lot heavier than aluminum when you got to pick it up. So they contain the valves. They contain the valve train, valve actuating components of the engine. So it may not contain all of the valve train. So the term valve train, and we got some pictures coming up, but the term valve train consists from the camshaft all the way to the valve. So anything between the camshaft and the valve is considered the valve train. So the valve train is going to be different based on engine design. So my valve train on a 1995 Chevy Tahoe with a V8 in it is going to be very different than my valve train on even a 98 Toyota Camry or a 95 Toyota Camry. Because the engine design is different, where we put the camshaft is different. I mean, so as we have these different differences, the valve train design can change. And we're seeing it evolve today as we start having some different computer controls going into the valve train and allowing us to activate and deactivate things. So we have cars that actually turn cylinders off and don't use them under certain operating conditions. So you have an 8-cylinder engine. Well, it's only a 4-cylinder right now, or it's only a 6-cylinder right now, depending on the manufacturer. And what they're doing is they're disabling the valve train for the cylinders they don't want to work. And they do that to save fuel. So we're adding more stuff to valve train. Valve train is not getting simpler, it's just getting different. So it went from having a lot of pieces to having very few pieces. Now we're putting more pieces in it again because we want the computer to be able to do things with it. But the term valve train includes the camshaft all to the valve and everything in between, whatever that manufacturer decides to put there. So it's kind of a generic term. It's not a specific to components. It's whichever included on that engine. So we have intake and exhaust ports to which the intake and exhaust manifolds are attached, and also the intake and exhaust valves will seal. Head sealing using a head gasket as a combustion chamber, either cast or machined into it. We have a couple of different designs. We have a wedge design, a hemispherical design. So we have different designs of a combustion chamber. So if I look here, this is more of a wedge design. I have a flat surface of the head, and I start here and go down to the deep end, and it looks just like a wedge, right? So I got a thick part of the wedge here, a thin part of the wedge here. My spark plugs would be exposed right here. And then I have an exhaust valve here and an intake valve here. So this is a very old school, traditional cylinder head design from a domestic manufacturer. And a lot of the manufacturers do something similar to that. What a hemispherical design is where I put the spark plug between the two valves. So instead of having a wedge like this, I've made a chamber like this. I've got the valves here and valves here, and I'm going to put the spark plug in the middle. And Chrysler started using this design back in the 50s. And they got way more power out of their Hemi engine than manufacturers did out of other engine designs. Very, very efficient design for power, much more complicated valve train system when you're using a single camshaft in the cylinder head. So that was the big detraction, because it was much harder to control and do, and adjustments were more time consuming. So it had some downsides from maintenance and complexity and cost to build, but from a performance and efficiency standpoint, it was huge. Well, once we went to putting the camshaft in the cylinder head, now all of a sudden the geometry of the valve train system to open and close these valves that are a V to the spark plug in the middle became very easy. And so that's why on modern vehicles, most engines today, I'm not going to use the word all because I haven't pulled everything apart. What I would expect to see when I take apart an engine made in the last 20 years is going to be a hemispherical designed engine, not a wedge shape like we see here. My intake valve is always bigger around than my exhaust valve, unless I have multiple intake valves to one exhaust valve. So in other words, the volume that the intake has to accommodate is greater than the volume the exhaust accommodates. So if I have 3 valves the same size in theory, I'd have 2 intake and 1 exhaust, which still gives me a bigger intake area. If I only have 2 valves, the intake's always going to be bigger. And we have engines that go anywhere from 2 valves all the way up to 5 valves per cylinder, where you have 3 intake and 2 exhaust. But we're always going to flow more on the intake side. So when I'm looking at this, I know instantly, hey, intake is the bigger around. So I can see here, this is where the valve would go in right here through the valve guide. And this is where the valve seals, which is the valve seat. And the valve drops right in here, is held in place.
Mr. Brian?
Yeah.
So what changed? I was going to ask that question. You kind of covered it. So when when a car starts coming out with, let's say 4-cylinder, 16 valve, what changes as far as performance or in general, what changes? Why was that designed?
Okay, great question. So, let's think about it as a room. We're all in a room and we want to leave. Would I be more efficient with one big door or make the door in half and have two different doors? Right? I'd probably be more efficient with two different doors than just the one big door. So that's what they're doing. So it's called volumetric efficiency. It makes it breathe easier. So what happens is with one big valve, even though I open up, the velocity decreases. So I'm not moving as fast through a big door as I would through two small doors. And so I want that velocity to mix the air fuel mixture, as well as that velocity increases my ability of my engine to breathe. Remember, our engine's just an air pump. So the better I can pump air, the more efficient I am. And what we found is by using multiple smaller valves as opposed to one big valve, I have better breathing, I have more efficiency, and that's why they do that. So I get more performance out of a multi-valve engine, but more importantly, I get better emissions.
And less stress in the engine.
What's that?
Less stress for the engine.
Yeah, I mean, it does have less stress because if I'm moving something really big, out, in, out, right? I've got that inertial or kinetic energy going down, coming back, going down, coming back. Now, if I have something smaller, I have less kinetic energy. Therefore, I'm going to, in theory, have less wear on my valves.
Got it.
And my parasitic losses are less. Remember, parasitic losses are where we're using energy inside the engine. I'm not able to use that energy outside the engine. So I've decreased my parasitic losses. Also, by having a smaller valve, I can make it move faster because I have less of that kinetic energy. So now I have an engine, instead of only being able to do maybe 4,000 RPM, now maybe I could do 6,000 RPM or 7,000 RPM because the part that is moving back and forth is smaller. That's, and that's true with valves. It's also true with pistons. If you look at a V12 engine and something like a Ferrari or a Lamborghini, it's not a very big engine. It just has 12 very small cylinders, which allows it to spin very fast and be very responsive and very smooth. Because you have less of that kinetic energy, so therefore I can go faster before I hit that maximum point where that inertial mass is too much for me to control and things start coming apart.
Perfect. I understand. Thank you.
Pretty cool, isn't it? Just how,
Yeah.
you think bigger is better. Well, no, depending on what you want to do, smaller might be better. But if I go look at a semi truck with a Cummins engine in it, a big old semi going on the wheel, it only has a 6-cylinder engine in it with huge pistons. Or are we trying to get there really fast, or are we trying to get torque, right? Well, we want torque. So what? I want that big inertial mass coming down and going back up. I don't need a lot of RPM. I need a lot of torque. So you see where what I want to get out really makes a difference. I mean, down to how you design the inside of something. How much? Yeah.
What the purpose is going to be. Yeah,
exactly. So it's unfortunately, sometimes people will buy one thing and try to make it into something else and get frustrated that it's not working and they're not understanding all the pieces involved. And maybe you're better off not doing that and going and getting what you really want. Stop trying to make the station wagon into the sports car.
I really like that analogy of the people in a room. That was really helpful. Thank you.
Good, you bet. I try. I'm a visual learner, and it's harder, here. So I try to use things that we're somewhat familiar with that we can visualize. So thank you for that. So which valve has the largest diameter head?
Number 1.
Number 1, intake.
Intake.
So my engine cam or camshaft. So I can have a cam and block engine or a overhead cam engine. So we have old engines, which I don't really get into here. Don't even cover anymore. I had to learn them. We put the valves in the block. And then we went to overhead valve engines. Cam was in the block, valves are in the cylinder head. And we still have overhead valve engines today. Then we went to overhead cam, where now I'm going to put the camshaft in the cylinder head. And we actually started doing that in the 60s on some cars. So we had an overhead cam engine. Then we decided it's even more efficient. Let's give the exhaust side of cam and the intake side of cam, and that's a dual overhead cam engine. So a dual overhead cam engine is not about how many cams are in the engine. It's about how many cams are on the cylinder head. So if I have a V engine that's a dual overhead cam, I would have 4 camshafts. That's a dual overhead cam engine. If I have an overhead cam engine that only has 1 camshaft for each cylinder head, but it's a V engine, that's a single overhead cam engine, because there's only 1 camshaft for each cylinder head, even though the engine has 2 camshafts. So I hope I'm kind of clear on that analogy, because it gets a little confusing sometimes. So the engines we see today are overhead valve, overhead cam, and dual overhead cam are the camshaft configurations that we see. So the cam is an egg-shaped piece, we call it a lobe, mounted on the camshaft. So just like our crankshaft, which had journals that went down the center, and then it had things that extend for the connecting rod to attach to buy leverage. In the case of the camshaft, we have journals that go down the center, and then we have eggs mounted on it like this, and the eggs stick up a little bit. So when they go around, they're going to push down on something or push up on something, depending on design. And when they come around to the other side, now whatever it is closed. So the valve's all closed, opens, closed. And it continues to do that. It goes around and around. And my wrist won't go around a second time, so I'm not going to. But we have the valve is closed, the valve opens, the valve closed. So there's 2 things we look at in the camshaft. One is the lift. That's how high we lifted. The other is, so that'd be a low lift, there's a high lift. The other is the duration. There is a very narrow duration or a very wide duration. So do I want to start opening the cam early, finally open it all the way, and then slowly close the cam? Or do I want to open the cam very abruptly, get it open and get it closed right away? So we have lift and duration are the 2 specifications we look at on a camshaft as far as the lobe. Then we take that lobe and we figure out how many degrees do we want that lobe mounted at, based on orientation to where the piston is going to be at top dead center. So that's our cam timing. So when they make a cam, we set our cam timing up on number 1 cylinder. And then using the chart like we saw yesterday, we know who has to come next based on the firing order, and all the cam lobes are shifted so that all the cylinders are going to work the same way cylinder number 1 does. So that is what our camshaft is doing. So the cam's timed the rotation of the crankshaft to ensure the valve is open at the correct time. So our timing chain, timing belt, or timing gears, we have engines that use timing gears, connect the camshaft to the crankshaft. And when we connect those 2, they have to be connected at a very, very precise point. If it's off just a little bit, the engine's not going to run correctly. So we have timing marks. Or we have special jigs and tools that we have to lock the crankshaft and lock the camshafts in position, then install the timing chain, and then tension it up correctly, make sure it's all installed. Then we take the securing jigs off, and now the engine's in time. But the engine has to be put in mechanical time. So when we talk about timing, there's 2 different kinds of timing. There's mechanical timing, that's by camshaft and crankshaft. And then there's ignition timing that I'll get into in the ignition section, which is when the spark is fired into the engine, into the combustion chamber. So many cars, especially older cars, we could do this on everything, I can adjust when the spark gets in the combustion chamber. I can adjust the timing. I cannot adjust my relationship between my camshaft and my crankshaft without disassembling the engine. Now we're going to see on modern computer controlled cars, the computer is adjusting the relationship for certain performance conditions and emission conditions, and we'll get into that shortly. But I still, even on those engines, I have to set that very, very precise relationship between the camshaft and the crankshaft. And as I mentioned, some of these take some really elaborate special tools to do that. And without the tool, you cannot do the job correctly. And so I have drawers of just special tools for putting together engines correctly. Because you can't do the job without the tool. And if you're in the business to do the job, you need to buy the tool. So that's just, life. So, as you're doing different engines, depending on the shop, many times the shop will buy the tool, which is what they should do. Other times, again, depending on what you're making and depending on what your position shop, maybe you're buying the tool. So I have a lot of tools. When I was doing a lot of work on European vehicles, a lot of BMW, Mercedes stuff, I have a lot of BMW setup tools from that vintage. I have a lot of those special tools when I owned a shop because I bought the tools as a shop. And when I sold the shop, I did not include the tools in my toolbox because I wanted those to make money with after I sold the shop. And I was real clear what didn't go with the business when I sold it. So those are the, so again, maybe if you're working on it yourself, you need to buy the tools to set that up. Do not try to put a timing chain on without using the correct tools if special tools are required. Some older vehicles, you just are lining up the gold chain link here with the gold chain and the dot here and just line those up, you're good to go. Very, very simple. Hey, I need to line the dot on the crankshaft to the dot on the camshaft, and when they're pointing, hey, I put the chain on, I'm in time. Very, very simple. Other ones are very, very precise and require specific setup tools.
I just had a memory back. So on the same Mitsubishi Mighty Max, when I did that engine overall, and I was setting up the timing chain in between the two, there was supposed to be a little special block that was keeping the tensioner in.
Right.
And I cut in a broom piece of wood and I drilled a hole in between and I put a wire. And so I used that as my tensioner holder so that I could accommodate the timing belt. And then I just jacked it out and it worked. It was so funny. It was creating that little tool.
No, there's different tools and different ways to get around things sometimes, but when it comes as far as tensioners and getting things set up, but when it comes to the setup, you really got to be careful with it.
Yes.
Even professional technicians put engines together that are out of time. And if I'm doing a timing belt on a car and it's a 2 or 3 hour timing belt job, that's not a big deal. I'm going to call my wife, tell her I'm not going to be home for dinner and I'm working for free tonight so I can make money tomorrow. Because I only got paid on what I did, not how many hours I was there. So if I did something wrong or something didn't work, I can't give the car back to the customer. And now I have a new opportunity to make that money again. So do I want to do it tomorrow when I need to be making new money, or do I need to stay late and make today's money still? And there's a lot of nights I stayed late because something went wrong and I need to make money tomorrow. And I just worked all day and it turns out what I thought I made money on, I didn't, because it's still broken. So at the very least, I need to figure out what I screwed up tonight. So I know where I'm at. I know what's going on, or I know what mistake I made. And, that's part of working on a commission basis.
I was a teenager back then. It was just for me. And remember how they used to have the auto parts, used to have the book, make and model of your car. We go get it. And that was pretty much our teacher.
No, and again, I mean, I did the same thing. I mean, I got into this business because I got a car. I liked working on my car. I had a bleeding ulcer at the time. And I couldn't do paperwork. I couldn't type things to reports because I just stress out. And I mean, I'd lost a lot of weight. And but when I worked on the car, I was able to do it and it seemed to relax me. And I had an opportunity through a friend of mine to get a job at a gas station. And I did that. And I just found that it relaxed me and I enjoyed it. And my ulcer got better and all those things. And so for me, still that physical hands-on really relaxes me. I do not enjoy doing paperwork. I don't enjoy doing those things. Not that I can't do it, not that I'm not even good at it, because I'm actually okay at a lot of it, or some of it I'm really good at. I just don't, it doesn't relax me. It stresses me out and I don't enjoy it. So life's too short to do stuff you don't like. You know, you got to find something that, you know, that you like, that you enjoy, and hopefully you can make a living at it. And if you can, then life is great because you're doing something you like and you're getting paid for it. I mean, there's nothing better than that.
Agreed.
And so, you know, unfortunately, you know, career counselors tend to try to figure out what you want to do, right? And then we go, oh, this is what I'm supposed to like. And you go do it and you hate it. And you go, wait, what's going on? What I figured out is a lot of life is figuring out what you don't want to do. And so for years, I wanted to own a shop, and I eventually did buy a shop. And we owned shops for about 9 years. It's what I wanted. It was my dream. It was beautiful shops. And what I realized, I was miserable and I hated it. So I got rid of the shops and went back to working for someone else, fixing cars, which is what I really like doing. So, you know, but it took doing what my goal was to figure out I hated it. And then it took me another couple of years to figure out, and a lot of money to figure out that it was okay that I hated it. And I wasn't disappointing myself by not doing it. So a lot of things that sound good, I mean, there's nothing wrong with trying it, but you also got to be willing to go, you know what, I just hate this. I don't like this. So, you know, that's why people ask me at home, why don't you own a shop anymore? Because I hated owning a shop. I didn't like it. Not that I wasn't good at it. Not that, you know, I couldn't make money at it. I just didn't like doing it. And I know other people that love owning a shop. They wouldn't want anything else. For me, I just didn't like it. That's why they sell more than one kind of car, right? Because we're all different.
A question about the timing belt.
Yes.
If you have a car that's new to you and it's a used car, how would you, is there a way that you can estimate the condition of it without actually going into the labor of replacing it?
Not really, unless you get records from the customer, or unless there's a sticker. A lot of times new timing belts come with a sticker that the technician can place on the timing cover saying it was replaced this day at this mileage. If there's nothing there about this day and this mileage, and there's nothing in the records, all you can do is open it up and take a look at it. If it looks brand new, then you can go, okay, it's probably been done. If it looks old at all, it's real hard to tell the difference between a belt that's got 40,000 miles on it and a belt that has 100,000 miles on it, because they just make belts better today. You know, back when belts lasted 60,000 miles, they start cracking and falling apart. You could really see the wear on it. But belts today are really made pretty doggone good, and they don't show wear the way they used to. Another thing you can do is if you walk the engine around, can you still see the brand and part number of the belt on the back side of the belt where it's been riding on the tensioner pulley? If the letters are still real bright and they look real good, it's probably a newer belt. If the letters are worn down or they're faded and I have a hard time seeing what brand or size, that's an old belt.
And taking a cover, it doesn't take a lot. Yes.
No, most engines getting an upper cover off the cam sprocket is not a big deal. It's normally about, you know, depending on the kind of car, but normally about a 10-minute job to get that upper cover off. And then at least you can walk it around. You can kind of get an overall, you know, idea of what's going on. Kind of look. You can also look to see if it's covered in oil, which would be a warning sign, things like that. What kind of car is it?
I'm looking into some Acura TL.
Okay. Yeah, they're easy to get the upper cover off. The only issue you have on the Honda products is many times the upper cover lifts underneath the valve cover like this. So you can pop it out, but you can't get it back in without loosening up the bolts on the valve cover, lifting the valve cover up slightly to get it back on and drop it back down. So just be aware of that.
Yes, yes, that's what I was aiming at because it seems it requires more disassembly than just, the cover. It's something more.
Right. Yeah, Honda puts the valve cover over the top of the timing cover.
Okay.
It's just what they do. So a lot of times you can get the cover off without taking the valve cover off, but you normally can't get it back on without taking the valve cover off.
Mhm.
That's why the valve cover is part of the instructions. But a lot of times you can, if the gasket's newer and in good shape, you can get away with just lifting it up and tightening it back down. If the gasket's older or you don't know, plan on doing the gasket because you got silicone that goes into the corners on a lot of those where the gasket goes up over the cam journals and there's 4 little spots on the dual red cam that you put a little silicone in to seal the gasket in place so you don't get wicking along that corner of the cam journal. And so you don't want to lift those up and pop them back down. The older single overhead cams, you could get away with it a lot easier, like the older Honda 1.5s and that.
So if we take the valve cover off and all that in this scenario, how far are we from doing a full timing belt job at that?
You're still a ways away because on the Honda, the big labor is getting the crank pulley off, getting the lower sprocket off, getting everything in time. So doing that, you're probably, I'd say 10% in.
Okay. Thank you, Mr.
I mean, you could say I'm wrong and it's 15 or 18%, but I would say 10%. By the time I'm putting the upper cover on and the valve cover on, I feel like I'm done with the job at that point. I mean, all the hard work is behind me if I'm reassembling at that point, because those come off really quickly by comparison.
Thank you.
Yeah, so, and the
just
harmonic
like to add
balancers
one
on
thing.
those are challenging to get off. They make a special holding tool for them because the bolt tends to be very tight.
Oh, I actually bought, it's a Lyle. It's a very heavy socket that, has that extra mass. You know what I'm talking about.
Yep.
So I'm looking forward to use it.
Okay.
I like to add that on those screws that you mentioned, Mr. Brian, where it goes up and it has that rubber seal and it's got 2 little notches, one on each side. I did that mistake. So if you apply whatever silicone base is required, make sure it dries up with the label and it dries up. So what I did, I put the silicone and then I just tightened everything and got the car on the road and that silicone was not dry, so it came off, it disintegrated. Then I started leaking oil.
Right. So with silicone, they have a cure time on them, and that varies by the type of silicone you're using and the quality of silicone you're using. And there is a full cure, and then there is a service time. So you can buy silicones that I can put it on, put the cover on, fill it up with fluid, and go drive the car. I'm good to go. There's other silicones that I need to wait 12 hours before I start that car and put oil in. So, when we're looking at different sealers, different silicones, it's really important that we use the one that is correct for the application. And failing to do that can get us create issues that we don't need or shouldn't have. And there's also color coding to the silicones where you have the gray, the black, and the red or copper. So it was interesting because I just did a Permatex webinar month or so ago on some of the new stuff they're doing with silicones and how they're using their products now. And I got to tell you, I was not expecting to learn anything. I thought it'd be blah, 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 blah. I actually learned some stuff from it and I got some stuff to share on that. So when we get into engine sealing, thank you for reminding me, Dante, I'm actually going to pull some of that stuff up and share some of that with you guys. So cam and block engines, I'm going to use push rods to transfer the camshaft's lifting motion to the valves by way of the rocker arms. Tappets or lifters. So there's another chance where we use the same component, 2 different names. So they ride on the camshaft lobes to actuate the push rods, rocker arm, etc. So tappets traditionally were mechanical lifters and lifters were hydraulic lifters. So hydraulic lifters are self-adjusting. Tappets, because they would tap when they became out of adjustment, required manual adjustment or a valve adjustment. So that's where the names come from. We use them synonymously now. If you're talking to an old guy, he's calling it tappets. You're talking to someone younger, my age and younger, they're calling it lifters. Overhead cam engines, camshaft mount on the top of the cylinder head. As I said, dual overhead cam means I have a separate camshaft for the intake valves and the exhaust valves. So here is a picture of a 4-valve cylinder head. You can see it's hemispherical in design where the spark plug's in the middle. It goes down evenly all the way around the sides. And I have 2 intake valves and 2 exhaust valves. So you can see here the intake valves are still bigger. Here is a camshaft. And here we have a main lobe. I mean, a main journal for the camshaft that rotates. And then I have 2 lobes here, 2 lobes here, and then another journal. So here you can see what I'm talking about by that egg-shaped effect. And so that egg-shaped effect, so there's a flat surface or a roller that's going to ride along this, which is the lifter, and gets lifted up and dropped back down. So we have 2 different types of lifters. One are a flat bottom lifter. So I have this cam that comes up, pushes it, and comes back down. That is a traditional design. We also have what's called a roller lifter. And that's where it's got a little wheel with bearings that's mounted to the lifter. And as it comes around, the wheel is actually traveling on the cam lobe. And that has some significant advantages. Less drag for one, less rolling resistance, so I can get more horsepower out of the engine and I'm not wasting the engine. Also slightly quicker response time because I'm not getting that drag, so it's a little more responsive to exactly where it is on the lobe because I have a smaller contact area. I don't have this big flat area that I'm going over and I'm moving across. I've got a real focused area that's just on the edge of that wheel that's rotated on here. So I've got a little more precise valve control. So we tend to only see those in performance engines, but that's what they mean by a roller lifter. As we look at a roller lifter versus a flat lifter, we have different lubrication requirements. So when I get in the lubrication section, I'm going to be talking about some of the different levels of oil quality and why we need to look at what oil we're getting in for what car we're using it in. So one oil is not hey, one oil works in everything. I have a lot of different engines here at the house, and I've got, let's see, 1, 2, 3, 4, 5, 6 or 7 different oils for the different engines I have here at the house. Probably at least 7, maybe 8 for the different oils I have, for the different engines I have here at the house. So you can see where it's not a one-size-fits-all approach. The oil has to be tailored to the needs of what we're actually lubricating. And that flat lifter versus a roller lifter has an effect on that choice. So here we can see a camshaft in the block. So the crankshaft main journals would go right here, and the main bearings would be set right inside here. And then the camshaft is directly above it. So this is an older V engine. Here is an older overhead cam engine. This is actually a Ford engine right here, using the Pintos and the Rangers and stuff. 2.3, 2.5 liter. And we see here where I have the cam lobe, and this is a newer one because it has a roller here. The older ones didn't have the roller. So it means it's after the Pinto. So you can see here, it has a fulcrum point right here that is hydraulically adjusted. It keeps this in contact with the camshaft, and then the camshaft rolls across, and then it opens and closes the valve. So our valves or valve train consists of a couple of different pieces. So even the valve has different parts to it. I should have grabbed my spare valve I had out in my shop. See if I have keys, I may still grab it. Actually, I'm gonna go grab a valve real quick to help with this. Okay, so as we look at a valve, this happens to be an exhaust valve. And I have the valve face. So this is the valve face right here. This is the machine surface. And this valve is really hard to see, but it's actually bad. And it's pitted. So this should be a real nice smooth surface. And it's actually machined. And in this case, it's pitted and has a whole bunch of pits in it. And that's what's causing an issue with valve sealing. And the pitting can happen from where? It can happen from carbon or other contaminants getting squeezed in. Because when we open the valve, it moves off the seat. And then when we close the valve, the spring, right here's a valve spring, pulls it back into the seat. As this is happening, the valves should be constantly rotating. So we make valves so that they'll actually rotate as they're going up and down. So they're not hitting the same spot every time. They're constantly spinning. So I have the valve face, and then next to the valve face, I have the valve margin, which is this area right here. So this valve margin is here so that I can dissipate heat. So if I have too little margin, so in other words, I could take this valve, I can recut this and make it smooth again. The problem is there's a minimum thickness of this margin. If this margin is too thin, the valve will burn. And when the valve burns, now combustion gases are going to escape past the valve and into the passage, losing compression. So when we grind valves, we set an angle here, normally 45 degrees. And then when we're done grinding the valve, we need to make sure we have enough of the valve margin left. If we don't have enough of the valve margin, the valve is junk, it cannot be reconditioned. So in this case, these valves were original, had 175K on it. I specifically asked when they did it, I wanted new springs, so I got new springs in it, but they recommended all new exhaust valves. My intake valves, on the other hand, were able to be cleaned up and reused. But my exhaust valves, because of the pitting, we would have taken too much material off and I would not have had enough of a margin. Now, I could have reassembled the engine with that, and it would have worked for probably 30, 40,000 miles till it burned a valve, maybe even a little longer. But it comes down to the longevity of the repair. So that's where sometimes getting something cheap is not the same as getting something good. So these are questions. If you take a cylinder head off, or you're taking something in to be machined, you want to be talking to them. You want to make sure they're checking the margin. Because if you got the guy that's doing the valves and, hey, we quoted out this cut rate price to do a valve job, do you think they're checking the margins? Do you think they're doing any of that? Or do you think they're just cleaning them all up, putting it all together? Does it seal? Yep. Have a nice day. And then we have a problem in a year or a problem in 2 years. And unfortunately, with machining, there's a lot of things that are hidden. All we know is we're paying a price for a valve job. Well, what's that valve job including? What are we doing? Is it a shop that's actually checking the things they should be checking? So when we look at valves, we have the valve stem right here. You can see how nice and clean this is. These stay nice and clean from about here up because it rides inside the valve guide. Up here is a little groove where some keepers get put in. They're two little pieces, drop in, hold a washer, and that's what keeps the valve spring in place. So I've got the valve spring right here. There's a washer and a set of keepers. The bottom of the valve spring is mounted to the cylinder head, and it is pulling this up. So between the valve face and up here, we have some cylinder head, and here's the valve. Here's the exhaust port or intake port. So I'm going to get carbon deposits on here. And you can kind of see the darker area here, on here, and on the back of the valve. So we're going to get carbon deposits there. The rest of this moves in and out inside the valve guide. And there's a seal that keeps a lot of oil from coming down, but we do need a little bit of lubrication. So it's not going to keep it completely out. But the valve guides are normally made out of brass. So we have a steel, very hard steel valve and a brass guide. So there is always going to be a little bit of wear there. And in this picture, you can see the spring I just showed you in the valve, along with the retaining washer and the valve keepers. So the valve keepers are held in place by the spring pressure, and this is tapered in here, and these are angled. So as long as the spring is extended, you have this V pushing up on the keepers that are locked into a groove. They can't come out. So if I want to get the keepers out, I have to compress the spring, the washer. I can drop the washer down, then I can get the keepers out, and then I can let everything come out with it. The other thing that should be done anytime a valve job is done is the springs are supposed to be tested. So there's a couple different things we look at for springs. One is what height are they when they're not compressed? And they should all be even. Also, are they square? So if I take a straight edge, like an L straight edge off my surface, is this square or is it tilted? If it's tilted, it's bad. The other thing that takes a special tool to do is this gets compressed to a specific height. And then the amount of pressure in the spring is measured at that height. And that's how we tell if we have a weak spring. Many places no longer do that. They're just cutting corners, right? Put it in, put it in. When I look at rebuilt engines, I can get a rebuilt long block and I can pay a huge difference in price depending on where I buy it. What some rebuilders do is they put all new valve springs in, or they test them to see if they're good. What other rebuilders do is they don't test them. What we're going to do is we're going to put a little copper washer underneath here. So we're going to what? Pre-compress the spring. Oops, that went well. Pre-compress the spring so that it has more tension on it. So even though the spring is worn out, because it's supposed to have this much pressure at this height, what if I make the spring now this height? It's going to have more pressure. It's going to close the valve. So rebuilders that do a poor, I'm going to call it a poor job, I'll be honest, but do a cut rate job, we use those shims instead of putting in new springs. Well, why would you do that? Money. How much money? I think a set of springs for my 6-cylinder engine cost me an extra $60, $50 or $60. So if I'm a rebuilder, I'm probably paying a little bit less than that. I did get it at wholesale. But you're still, what are you talking, $50? Well, $50 is a lot of money if I want to sell you an engine for $1,000. That's $50 a profit. How much does 12 washers cost? A lot less than $50. So those are things to look at. If you're buying a long block and you see the washers there, that's a concern to me, because that means they didn't do the job correctly. Those washers weren't there when it left the factory. Why are you putting them there now? Because you didn't service the components that should be surfaced. I put all new springs in my Jeep, not because the machine shop recommended them to me, but because they had 180,000 miles on them. And I want the thing to go another 100 and something thousand miles without a problem. And I know from the pitting the valves, one thing that causes the pittings is the valve moving too much because the springs get too weak. So I want everything to work correctly. So if I'm spending, what's the difference between spending $450 and spending $510? I mean, once you're in that far, might as well go all the way. So these are things to keep an eye out for. And again, having been a certified machinist for engine cylinder head rebuilding and having done it in the shop as part of my day-to-day work, these are the things I see people cut. These are the things I see machine shops not do correctly. That's why I'm very picky on which machine shops I use. And that's also why I've, deliberately, told customers up front, I'm going to need the car extra days because I won't use the shops that are close to me, or I won't use other stuff because I know what I'm getting with where I'm getting it from. I want it done right because we only want to do this once. So these are things to ask. Don't assume just because someone calls it a valve job or someone says they're doing your cylinder head that they're all doing it the same way, because they're not. So these are things you need to kind of look at. What's being done? If you're doing it yourself, these are things to consider. Also, many times these valve springs, just like this one here, are directional. They don't go either way. There's a slight taper. Sometimes they are directional. They aren't directional. They can go either way. Other times they are. So it really comes down to the specific spring. So it's careful to look at them. Valve opening is controlled by which of the following components?
Number one.
four.
Number four.
It
Number
would be
four.
number 4 controls the opening, right? So the timing of the opening is controlled by the timing chain, timing belt relationship to the crankshaft. I was looking for number 4 camshaft. The valve opening is controlled by the lobes on the camshaft, was the thought process. If you jumped ahead to crankshaft, you're thinking, well, because the crankshaft's turning, it's connected to the timing chain. which in turn is turning the camshaft, and that's what makes the valve open. You're thinking big picture. I'm not going to say you're wrong. You're 100% right. You just thought about it a lot more than I was looking for in this question. If you said crankshaft because you're confused, then I'm glad I said camshaft. But yeah, what I'm looking for in this question is camshaft, because that's where the lobes are. So the valve open is controlled by that. And the reason why I think the camshaft's the best answer is going back to that lift and duration. So just because I'm spinning the camshaft, if I don't have correct lift and I don't have correct duration, the valve's not going to open correctly. And camshafts will go what we call flat. That's where the lobe is no longer as big as it should be and gets too short. And we do see flat cams. Not as common today as it was 40 years ago. But engine design and lubrication have gotten a lot better than it was 40 years ago, but it does still happen. And I mean, I just had one, I keep forgetting how long I've been at the school, probably been 5-6 years ago now, but it was a late 90s BMW with a flat cam. It wasn't all the way flat, it was just a little flat. And it was causing the car to fail a smog inspection. No codes. Computer thought everything was great, but the car wouldn't pass smog. Customer had already put a bunch of parts on it, making the problem worse. But the root cause was a bad camshaft lobe. And so I was able to see that, explain that to him, told him to undo all the other things he did, and it needs a camshaft. And that was the reason for it.
A question about machine shops, Mr. Bryan.
Yes.
So for example, I've had a couple of times that my head gasket had a leak, so it had to be disassembled and the head had to be sent to a machine shop.
Okay.
So what is that they should do at that time, other than checking for trueness or whatever you call that?
So if I have a head gasket that's leaking, and I assume you're talking a coolant leak or an oil leak?
It was an exhaust leak into coolant system.
Oh, that's very unusual. Normally that's more of a crack. But okay, so I would definitely I would let them know, hey, we're getting exhaust in the cooling system, or it could be combustion gases in the cooling system. So normally if I send a head out to the machine shop, I want it checked for surface and I want it checked for pressure. And they don't necessarily automatically do the pressure check because each of those has a separate charge. So if we need to surface the head, that's going to be one price. We need it true. But what we want is we want them to take the cylinder head, and the valves are closed, and they put inserts or spark plugs into the spark plug holes. And there's a plate that bolts onto the front of it, like the block would. And then it is put into water, and high pressure air is put into each of the cylinders. And then they look for bubbles because it's underwater. If you get any bubbles past the valve, it needs a valve job. If you're getting bubbles through a coolant port or something like that, then that would also indicate a crack or some other kind of issue. So in the old days with cast iron, we used to do what's called magnafluxing, where we would put a magnetic charge in, sprinkle powder, and the powder would go to the crack. That can still be done. It may occasionally be done on antique stuff, but most shops today, what they're using is a pressure tank, because we're really looking for pressure to move. And they can block off the coolant passage and do that, block up exhaust ports. They have a lot of capacity to look for that leak. So they can do it at the exhaust ports, put in air there, intake ports. So they have a lot of different adapters for different engines, so they can pressure test the head. But the two things when I send a head out to a machine shop is I want it checked for, straightness, cracks obviously, but leaks and cracks, and then, trueness. And then I want to get a phone call with what we need to do to it. And when I quote a job, say I'm taking the cylinder head off of your car, I'm going to quote the labor for me to take it on and off, the parts I will need to put it back on. So the basic gaskets, oil, coolant, those kinds of things. And the labor the machine shop is going to charge to do those tests that I wanted to do. And I'm going to explain to the customer, once I get the engine apart, once I hear from the machine shop, I'm going to give you a call and let you know how much more money we need to spend on this car. Because what are the odds I'm going to take the cylinder head off and not find any hoses broken, any spark plugs worn out, other things that would be good to do while we have it apart, right? I mean, you're not paying any more labor. Do you want me to put the new parts in or the old ones in? That's the time to have that discussion once you get the whole picture. The other thing that happens sometimes when I pull the cylinder head, and I've had this happen a couple of times, I'm going to check the straightness of the block. And I've had blocks that aren't straight. That's a whole different story, because now we're talking about an engine, or we're talking about pulling that engine out and having the deck remachined, which you can't always do. It depends on engine design. And now we're into a full rebuild, but I don't know that till I take it apart. And the state of California says my labor price has to include removal and reassembly and the parts needed to do that. So if you wanted me just to put the head gasket back on, I can do that. I can reassemble it. It may not work properly. It may still leak, whatever, but I'm meeting the requirements of the law. And that's, that's the legal one. But back to your original question, Bronco, that's what I'm looking at is, I want a pressure test, and I want to check for straightness. I mean, what am I looking for here? Do I have a crack? Do I have valves that aren't sealing? Do I have a warped head? What do I have?
And when you said now that you're checking the block, also that's done with the straight edge on the block, right?
Correct. That's done with a straight edge on the block. And I use a feeler gauge. So I'm going to use a feeler gauge with a long straight edge. And I'm going to go diagonally one way, diagonally the other way, and then at the far straight across, in the middle straight across, and towards me straight across. So I'm actually looking at 5 different measurements with that long straight edge. If I see something looks funny, I may turn it sideways and try to go across this way on different parts of the block. But normally those 5 ways will tell me if I have an issue with the block. And some engines, Honda and other manufacturers, use what's called a sleeve. And that sleeve sits raised up with coolant all the way around it. And that sleeve is set into the casting. And what happens sometimes is those sleeves will drop. And if they drop, then you put the head gasket on, you're not going to seal around that cylinder and you get combustion gas in the cooling system. Very common if a car has been extremely overheated. That can't be fixed. You are done. You need a block. Now, on some older vehicles, like we did a Jensen Interceptor from the 60s, those barrels are actually set on layered cardboard. And you actually take it out. It's cardboard shims. You take it all apart, you reset it, you reset the shims, you pack it down, compress it back down, take your measurements. You can actually adjust the height and you can compensate for it on this old Jensen Healy we were working on. So there's some old stuff that really wasn't made as well, but is much more adjustable. And then we have newer stuff like Honda that once it's done, you got to throw it away because there's no fix in it.
Thank you.
You bet. But that's what I look for in a head. And I won't, I've gotten this into where I've had bosses or service writers. No, they just want the head gasket. They want the car back today or tomorrow. I'm like, I won't pull the head without it going to the machine shop. Or you can check it for straightness. You're right, I can. I'm not going to guarantee it. If I make a mistake, it's on you. I want it to go to the machine shop. So if you don't want it to go to the machine shop and this car comes back with a problem, I'm getting paid again, just so we're clear. Because I told you we need to send it out and have it pressure tested. I told you we want to send it out and have it, all these things done. If you don't want me to do those things because the car was running and all we're fixing it is for an external leak or we're doing whatever, that's on you. But I'm looking at a car with 130,000 miles on it. I'm telling you what I recommend. And what's amazing is I have yet to have a boss double down and say, nope, I just want you to do it. As soon as I explain to them that I'm not going to stand behind it because you're not doing what you should do, and it's on you and I will get paid if I have to do it again, all of a sudden we're sending it to the machine shop and I can get the time. And I tell you, 9 times out of 10, it's needed work at the machine shop. Even if it's a simple surface, but many times, especially 135K, it's a surface in a valve job. May even be new valve guides or new valves, I mean, whatever. But what's the customer expect? If I take the cylinder head off of your car, I'm taking the top end of your engine off. How long do you think that repair should last before we have to take that engine back apart?
Probably as much as it lasted before it broke.
That's what I would think. I think that's reasonable. I mean, if it's 130,000 miles now, I think you'd be pretty upset if we got to take it back apart at 180,000 miles. I don't think the customer would be happy with that. I don't think we would meet expectations. So since I know what the customer expects, I better do the job that's going to have the best chance of meeting that expectation. I mean, certainly if I rebuild the top end at 130,000 miles and the bottom end goes at 200,000 miles, I didn't fix the bottom end. Right? The bearing went bad, started using oil, piston went bad. That's something else. You know, that's something that, again, is part of that discussion you have with the customer. How much do you want to spend now? What are we trying to get? What are we doing? That's a discussion transparency issue, but the customer is not going to blame me at 200,000 miles, 30,000, 70,000 miles later. It may be 3 or 4 years that they need to take that it now needs an engine. They got 3 or 4 years out of the repair I did, and there's nothing wrong with the repair I did. So that means I met the expectations the customer had on the job.
So the machine shop, when they pressure test, they will actually detect the need for the valve job. Is that
Yep,
okay or not?
exactly.
Mhm.
Yeah, because they're looking for leakage. And what I can tell you is when the valves seal, there is no leakage. So if there's any bubbles, any leakage, it needs a valve job. Done.
Okay, that's how we come to a valve job at the
Mhm.
machine shop. Okay, thank you.
Yep. So like on mine, I knew my valve was leaking intermittently, but I knew it was leaking. And so I told him, look, I know it needs a valve job because I have this cylinder leaking. I still want the cylinder head checked because I don't want to do a leaking valve in case maybe it wasn't the valve and it's a crack in the head, right? I mean, so my ego's not so big that even though I diagnosed it as an exhaust valve problem, could it be something else? Yeah, I could have a cracked seat. I could have a hairline crack in the head. It could be something other than just the valve seating. I am not the expert. I don't have the tools to be that expert. What I want to do is have them do it. Now, what I did on mine is I actually did the old school. I flipped it upside down on the bench, poured some water, put the spark plug in, poured some water on it so that the water level was level with the deck surface of the head, because the head's upside down, and waited. It took probably 20 minutes, 20, 30 minutes before water started coming through where the valve itself was leaking. So I was able to verify it before I set it off. And I already knew it was. I did it just to take some pictures so I could put them in a PowerPoint or do a presentation with them. So I did it just to get pictures out of it. But that's something we can do at home. Keep in mind, because of the carbon and everything, the water wants to bead. So it takes quite a while for it to finally seep through something. So it's not going to be instantaneous unless it's a huge problem. Oil or solvents actually work better for checking that because they're not going to bead the same way. They're harder to clean out, more expensive. So normally we just use the water. But again, you suspect it. Don't think, hey, it's been 2 minutes, it's not leaking, I'm done. No, you gotta wait. Give it some time. So if I'm doing a whole cylinder head, I'll put spark plugs in, I'll fill up all the cylinders, walk away. I'll come back and look in an hour. Did any of them go down? Do I have any water coming out the bottom? So it's not a 5-minute home check. It's something you got to be patient with, but it is something you can do some preliminary checks at home. It's not as good as the pressure tank. That's why they spent all the money at the pressure tank at the machine shop. But I can certainly tell something horrible at home. So it is something I have an option of doing. So probably gave you more information than you wanted, but I tried.
No, this is actually excellent. I'm so glad I asked.
So mechanical and hydraulic valve train. The valve train is a combination of parts that work together to open and close the valves of the engine. Valve train operates off the camshaft, and the part that rides against the cam lobe is the valve lifter or tappet. The lifter is a mechanically solid piece. It is a mechanical lifter. If it has parts inside, it's a hydraulic lifter. If it's a solid lifter, it has a mechanical valve train that requires adjustment. If it's a hydraulic plunger in the center, it's a hydraulic self-adjusting valve train that normally has some sort of assembly procedure. Once it is assembled correctly, we're done. It never needs to be adjusted. So any noise from that valve train or failure of the valve train indicates a failed component. So we have rocker arms. And here's the lifters. So I talked about the flat lifter and the roller lifter. This is what I was talking about earlier. Here's my rocker arm. So my lifter would be connected to a push rod. The push rod would push this part of the rocker arm. This part of the rocker arm would push on my valve stem to push it down to open it. If you notice, we are not equal here. This sticks out further than this does. So this gives me the advantage of leverage. I'm able to push up on this. And this is normally, this looks like a Chevy, so it'll be a 1.5 times the stock. 1.5 times. So whatever this moves, this is going to move 1.5 times as far. For Chevrolets and some other race applications, they also make a 1.6 times and a 1.7 times. So I can increase the amount of lift without changing the cam. So again, like anything, you get into performance, you can start playing with stuff on certain engines that are popular for performance because parts are available. This one's a little bit different in that it has a bearing in here. Again, we're getting rid of parasitic losses. I have a bearing here. I have a bearing here on a roller. I'm going to have less drag in the system shown on top than I would on the bottom. The one on the bottom, you see how this is rounded. Inside here, this little piece that you see the bottom of right here is rounded and has a couple grooves in it for oil to travel in. And it's just a metal on metal pivot with a couple slots for oil to keep it lubricated. A lot more friction than this fancy bearing, which is also lubricated by oil. So here's a cutaway of an overhead cam engine. So here's a camshaft. Here is where we have a roller called a lifter if you want. It's actually part of the rocker arm. We have a roller that rides on the cam lobe. You can see the edge of the roller right here. Over here, we have a pressurized hydraulic lifter. You can see the little hole right here where the oil is allowed to escape because we're constantly supplying it with pressurized oil. And it pushes down on the valve stem. Here's the washer I was talking about. Here's the spring. There's the stem. And inside the stem, I have the valve guide. So here's the valve guide. Here's the valve stem. On top of the valve guide, we have a valve guide seal. So if you have a car that smokes a lot on startup, it's normally a bad valve guide seal. It's not the rings. If you have a car that smokes a lot at idle, or if you're sitting there idling a light, then you hit the gas and you get a whole bunch of smoke, that's normally valve guide seals on the intake valves. If you have a car that puts out black smoke on acceleration, that is not the valve guide seal causing the oil smoke. Actually, be more white smoke on acceleration, excuse me. Black smoke would be fuel. White smoke on acceleration, we're looking in its oil, not coolant. So it's gonna be grayer than white. But if it's oil smoke on acceleration, that's bad rings. That's not the valve guide seals. So of the things that cause cars to smoke, valve guide seals is the most common. Rings do wear out, sure. And you can see that when a car is smoking on acceleration and there's oil smoke coming out. Because that's when we put the most pressure on the rings, is under acceleration. At idle, I have what's called intake vacuum on the intake port trying to pull oil down the stem. So if I have a bad seal, I'm going to pull a lot more oil. That's why I'm going to have smoke at idle, or if I initially just snap the throttle right after the car's been idling, that's valve guide seals only on the intake. If the car smokes when I start it up after sitting, that means that as the car sits, the oil that's all over here has run down the valve stems, intake and or exhaust. And now when I start the car, I've just killed a bunch of mosquitoes for about 30 seconds. And now it's not smoking anymore and I can go off my day. That's valve guide seals. Valve guide seals can be replaced without removing the cylinder head. So that is something that can be done without taking the cylinder head off, which means I don't need to, take the top half of the engine off the bottom half of the engine. Depending on the engine design, they can either be a fairly quick job, couple hours, or they can be an extremely involved job requiring special tools, such as on a BMW. So it really varies by application. The valve guides, excuse me, they also wear out. And so one of the things the machine shop does when they're doing the valve job, or if they disassemble and inspect for a valve job based on leakage, is they actually check the tolerance in the valve guide. So there's actually a specification with the valve in the guide, how much back and forth play you're allowed. And what you do is you actually take the valve out, install it in the other way. So you got leverage, you're a certain distance up above, and you can measure the amount of play in there. As the valve guides wear out, you're going to do two things. First of all, you're going to create leaks. So you're going to start using oil. You're going to get some of the same symptoms we had with valve guide seals. But more importantly, we're going to destroy the valve guide seals because we have too much movement for the seal repair to last. So those are the issues that we see with valve guides. They are replaceable separately. So the machine shop can put new valve guides in. And that's our routine service. When we look at valve clearance, we're adjusting the amount of slack between the rocker arm and the valve. So on the valve stem. So if we look here, we're doing a manual adjustment right here to the valve stem of the valve, and there's a clearance between here that's specified by the manufacturer, either hot or cold. If they use the word cold, they normally mean under 100 degrees Fahrenheit is considered cold for a valve adjustment. The exception would be old air-cooled Volkswagens, which actually want cold. You haven't started it yet today. This is a hydraulic lifter. It uses a self-locking nut. This happens to be Chevrolet. And we adjust this nut to set the correct preload on the hydraulic lifter using manufacturer specifications. And so at this point, I'm going to get into adjusting bucket style valves and talking about this a little bit, but I want to spend some more time also talking about doing a mechanical adjustment. So I'm going to take the opportunity to probably grab some tools out of my toolbox and some assortments to show you guys some stuff tomorrow and talk about this a little bit more. And then we will also be getting into camshaft timing tomorrow and some timing chains, how we check for a worn timing chain, and get into the function of our variable camshaft timing and why we do it, how we do it. And let's see, depending on where we're at, we may also get to rotary engines tomorrow. So kind of see how far we get, depends on questions and everything.